today we're going to talk about 12.2, which is vectors. Okay, look at my picture here. The tree here, kind of like an arrow pointing up. Okay, that actually is a symbol for vector. The term vector is used by scientists to indicate quantity, for example, like velocity or force. We know that velocity has magnitude, right? How large is the velocity and also has direction. It's an example of a vector. A velocity is an example vector. And similar for force. Force also has magnitude and also has direction, right? So it had two things. So velocity. So velocity and force both are vectors. You need two things. Well, what are the two things? You need a magnitude and also you need direction. Okay, so those are vectors. And the way that you represent vector is by arrow. This arrow right here. Okay, you see this arrow right here is an arrow, and maybe turn this off. Okay, an arrow, and then with the length of this arrow is the magnitude, and the direction is what the arrow pointed. Okay, so this is a vector. Okay, usually you denote a vector by a bold-faced letter. For example, this V over here, as you can see, this is bold-faced. Okay, so it's bold-faced V. Okay, another way to represent that is like this. Put the V here, and then you put an arrow on top. That will indicate a vector. And for you guys, remember, example vector include velocity and also force. Now, different from vector, we call that scalar. Okay, what's a scalar? Scalar is, for example, it could be speed. Well, how speed is related to velocity, that is the magnitude of the velocity. So the absolute value here stands for the magnitude. Okay, remember, that is the magnitude of the velocity. And for example, like 50 miles per hour, that is the speed. Okay, it doesn't have direction. Okay, it's called scalar. So what are the difference between a scalar and a vector? Scalar doesn't have direction. Vector has. Okay. Now, suppose you have a particle move along a nice segment from this point A to point B. Then what happened over here? Then you can indicate, you can use this vector. It's called the displacement vector. The displacement vector is going to go from this point A and then point it to point B. This is a displacement vector. So you move from A to B, the displacement vector will go from here to here. That's a displacement vector. The initial point of this is A, and the terminal point is B. Initial point also called the tail, and the terminal point called the tip. Okay. Now notice that over here we have two vectors, U and V. Notice that the U here go from C to D. Compare these two vectors, they have the same length and the same direction. Okay, well, it also points that way. And even though the position are different, right? Now, however, we call them equivalent. So the two vectors here are equivalent. Okay. Now, when I first encountered this, I have a hard time thinking about, well, they're at different places. How do you call them equivalent? Well, think about this, like you have, think about the, my Apple Pencil here. I put it here or I put it here, it's still the same pencil, okay? It just move in different position, position. So it's still the same vector, okay? So imagine that. So these two vector u and v will be the same. It just have different position. You can put it here, here, and here, but it's the same vector, okay? So remember that. Okay, now, and then we say the two vector equivalent, and we put u equal to v. So these are two equivalent vector. The zero vector is denoted by zero with a both face. Okay, let me emphasize. This is going to be both face. Now the way that you indicate this, if you don't want to make it both face, you can put a zero there and you put an arrow on top. That is a zero vector. Okay. What will be the length of the zero vector? It's going to be zero. Yeah. So it's going to be zero. Okay. And that's the length of it. What's the magnitude of a zero vector? It's going to be zero, right? It is the only vector that has no direction. Okay. The zero vector is the only one that has no direction, right? There's nothing, right? No, you can put, okay, so no direction for the zero vector, and that's the only one. Next, we're going to talk about combining, okay? Combining vector. Okay.
Sure.
Yeah?
For the zero vector, what is it used? Like, is it just supposed to represent like zero?
Remember when you indicate nothing, you have zero, right? When you indicate you didn't go any direction, then you have a zero vector. Okay, just like what the number zero for. You need there. Sometimes the vector go this way, but then you go back and it cancel out, and you resulting in a zero vector, right? So you need the zero vector to indicate that. Okay.
And it has no magnitude.
The magnitude will be zero, but the direction, there's no specific direction, right? Zero vector has no specific direction, okay? All right, now we're going to talk about how to combine vectors. So suppose we have a particle that moves from A to B. It moves from A to B. Okay, so the displacement vector will be starting from A and point to B, right? That's the AB displacement vector. So you can indicate AB and put an arrow on top. That's a displacement vector. This particle, and then after that, if that you move from A to B, and then after that you change direction, and then you're going to move from B to C. Okay. So then what will be, okay, so the BC, and put an arrow on top is another displacement vector, right? So you go from A to B and then from B to C. Then what do you think about the combined effect of these two displacement vector? They'll be from where to where? Starting from A and ending at C, right? So if you walk from here to here and walk from here to here, then the result here is the same as you go from here to here, right? The final result is go from A to C. So A to C, this displacement vector, is the sum of this vector A to B and B to C. That is the sum of this and this. Do you guys agree? Okay, all right. So now we're going to talk about how to add, okay? So if you add two vectors, okay, then the sum of it is the vector starting from the initial point of the first one and then to the terminal point of the second one. So if you have from here, you have a u vector and you have a v vector. If you add them up, it's actually starting from the beginning, the initial point of the first one, pointed to the ending point of the second vector. Okay. Now, and you can see that these three form a triangle. So we call this kind of addition is using the triangular law, right? It's a triangle. So that is a triangle law. Okay. So maybe one more time. Okay, let me indicate that. So you have from here, this is the vector u. And then after that, you're going to add another vector. You're going to add another vector, v. Then the result, the sum of these two, will be starting from u and pointed to the tip of the v. So this is u plus v. Got it? Okay, so this is the sum of the two vectors. Just think about you go places, right? Go from here to here and go from here to here. The result is the sum, and you go from here to here. Okay, it's called the triangle law. Another law is called the parallelogram law. So another way to do it. Okay, so okay, let's put the triangle law first, right? The triangle law, and how does it do? So you go from u, and then you go from here, and then you put the v over here. This is u plus v. Now, the parallelogram law, which is this one right here, how does it do? Okay, let me explain to you. So you have this vector u, and then you have this vector v, but this time, remember, well, I'm going to put that v over here. Remember, it's the equivalent. This v over here and this v here are equivalent, right? They have the same direction and same magnitude. So we call them equivalent. So we can put the v, so then the initial point align with this initial point of u. Okay, so the v right here. Now after that, we're going to get a parallelogram. So the parallelogram right here, right? Then we draw a parallelogram. Then after that, the diagonal here is u plus v. Do you think these two are the same? Are they equivalent? This u plus v, this u plus v, are they equivalent? Yeah, they're equivalent. They're just at different position, but they're equivalent, right? So you get the same result. So this is called parallelogram law. So two ways to add the two vectors. One is the triangular law. The other one is parallelogram law. Which one you guys prefer? Huh? Oh, you have parallelogram? Anybody like triangle law? Yeah, you like triangle. Yeah, I like triangle law. Okay, this is a free country. Okay, you can choose which one you like. Okay. Yes.
Yeah. So the two ways of trying to add together according to the hypothesis. I think this is the Pythagorean theorem. The hypothesis is not equal to two wings of the triangle being added together.
Because they're not right triangle. This is not right triangle, so you don't use a Pythagorean theorem. Yeah.
Oh, yeah.
Okay.
This doesn't work for Pythagorean.
No. The angle here is not a right angle. Not Pythagorean theorem. Okay. Yeah, I'm glad that you asked. Yeah. Good observation. They also derive from actually the v here and the v here. They're actually equivalent. You can move the vector to any position. You still consider them as the same vector, equivalent vector. Okay. Right. So you get the same result, u plus v. Okay. Okay, now let's do some examples so that we can feel more comfortable with this addition of vectors, right? Okay, let's look at the first example. We're going to draw the sum of the vector A and B, right? These two vectors. How do we find the sum of these two? Okay, I'm going to copy the vector A here, okay? And then I'm going to copy this vector B. Let's try two different ways, right? The first way, I'm going to use the triangle law. Okay, let's do the triangle law to do it. Okay, so we have vector A, and then what should we do? I'm going to copy this vector. I'm going to copy this vector B, and I'm going to put this one over here, right? Okay. Please. Now I'm going to put it over here. It broke a little bit, but You see it? Right? So this is vector A. This is vector B. So I first have this vector A, and then at the tip of it, the terminal point, I'm going to put the vector B. So continue with vector B. So I first have vector A, and then I continue with vector B. What will be the sum of this A and B vector? What?
Vector A plus vector B.
Yeah, vector A plus vector B will be starting from the initial point of A and point it to the terminal point of B. So according to the triangle law, that will be A plus B, right? Okay. So all you have to do is just put the vector B here, okay, at the ending point of this A, and then you will get this A plus B. Oh, it's actually right here. You see it, right? The same result. So A to B. Now, if you do the parallelogram law, okay, the parallelogram law, I'm going to do it. So I will start with this vector A, okay, and then for vector B, I'm going to put that at the same. Remember, we put that at the same. The initial point put at the same as the initial point of A. So I'm going to move it. Yep. Sometimes it doesn't listen to me. I want it to move. Okay, right here. Okay. So, and notice that right here, they actually put it at the same point, right? So the same initial point. Put it at the same initial point right here. Okay. So here's A, here's B. Then what will be A plus B? Then you will construct this parallelogram. Okay, parallelogram. And then this diagonal right here is A plus B. Now compare this with the triangle law, right? Do you see the two are the same, right? Are they equivalent? Yeah, equivalent. Okay, so you can do either way. Question? Okay.
So you can assure that the two sides A and B add together between the diagonal that goes across the parallelogram.
Yes, the result of the two vector will be this one. The vector that go across the parallelogram, starting from this initial point. Yeah, that's A plus B. Okay, now we talk about combining vectors, continue. Okay, now you see over here, let me enlarge it. What happened over here is I start with this vector V and I multiply that by 2. And what does it do? It double the magnitude, right? And if I multiply by 1/2, and I can just shrink it, right? It scaled down to 1/2 of the magnitude, right? If you multiply this by -1, I get negative V. And what does it do? It switch the direction to opposite, right? And then similar times -1.5. Now you can see that what happened to those numbers? Those numbers, what does it do to the vector? The multiply by that number actually scale that, right? Either scale down or scale up, right? So for that reason, we call the real numbers that multiply with those vectors, we call them scalar, okay? So those like 1, 2, 1/2, -1, -1.5, those are scalar. So it's just another way to say real numbers, okay? So all real numbers are scalar, okay? Scalar, okay? And here, those are scalar multiple of this vector V. It could be a negative scalar, right? It could be positive scalar, okay? So another way to call real numbers, and you can call them scalar. Do you guys notice that in this diagram, you see that they're all parallel, right? Are they parallel? If you have scalar multiple of them, are they all parallel?
Mhm.
Yeah. So, and they're parallel. If they're scalar multiple each other, then they're parallel. And if they're parallel, they should be scalar multiple each other, right? Okay. So except the zero vector, okay? So now, so we say that two non-zero vectors are parallel if they're scalar multiple of another, okay? So remember this result, okay? So if we're parallel, scalar multiple each other. Now, in particular, you can notice that over here, the negative v, right? Negative v is the same as -1 times v. It has the same length of v, but it points to the opposite direction. So we call it the negative v. So when we do subtraction of vector, or we do the difference of the two vector, u minus v, we can think about that as a u adding with the opposite of v. So you can do it that way, okay? So that's u minus v is the same as u plus negative v. Okay, now we can try to look at the diagram and understand that, okay? So what's u minus v? So I start with this u here. Let me make it, okay? So I have this u over here, right? This vector u, okay? And then I'm going to subtract v from it, right? So when I subtract v from it, then it's the same as adding negative v. Now I know that v go this way, right? V, let's say, this is v, okay? V go this way, this is v, okay? Now, but I'm not adding them, I'm subtracting, okay? So what I do here, I'm going to take the v and make it opposite. So this one here is negative v. The orange vector here is opposite of v or negative v, okay? Now, when I add the two vector, over here, I'm using the parallelogram law, right? This one here, I'm using the parallelogram law. And you can see that the resulting vector will be this one. This is u minus v. You see it? Okay. Some people say, oh, okay, let me color code it better. The u here, I'm going to use the blue color. This is u. And then I adding the opposite of v. Then this one is the result. You guys see it? Okay. So this is u, okay?
So if it were u plus v, it would go from that blue to green?
Yeah, okay, good question. Let's think about what's u plus v then. U plus v, and then you're going to construct the parallelogram this way, right? That way. And then you're going to get, let me use a different color. This one over here is u plus v. The purple is u plus v. The red one here is u minus v. How about we use the triangle law? How about we use triangle law over here? Okay, so we start with the u. Yeah, so we start with the u right here. Okay, start with the vector u, and then I'm going to, now the v go this way, right? So the v go this way, but then I'm going to do the opposite of v. Okay, so I'm going to opposite v, that will be this way. This is opposite of v. Okay, then according to the triangle law, then it's going to be this. This vector over here will be u minus v. You agree? Right? The triangle. However, you know that this one and this one are actually this one. Okay, let me highlight this. This one right here and this one, they're actually the same. These two are the same. It's just a different position, right? So this is the triangle law, okay? But so in any case, you can see that the u minus v is this. So when you try to have u plus, when you try to do u minus v, you can just use u plus opposite of v. to get that. Okay, so practice on this one. Okay. Now, however, maybe we can have a shortcut. Okay, let's think about some shortcut. So I start with the vector u, right? And then I have this vector v. Let's try to summarize it and then have some observation, right? So what's u plus v? U plus v, okay, let's construct a parallelogram. U plus v will go from here to here, right? It's this diagonal, right? Do you guys agree? Okay, so this one over here is u plus v. That's the one, okay? Now, what about u minus v? U minus v is actually the other one, okay? I need to think about what color should I use. It's actually going this way. Okay, it's the other diagonal one here. This is u minus v. Okay? Yeah, this u minus v. Okay? Oh, maybe I can use this color here. U plus v is purple. It's this one. U minus v here is the red one right here. U minus v. Okay? So in the same parallelogram, you can see u plus v is this. U plus v is this diagonal. U minus v is this diagonal. Okay? Question? Yeah.
Doesn't it start at u? Sorry. Doesn't it start at u instead when you're subtracting v? Because you're supposed to start at the tip of u. And then the tail of v. You said u minus.
Yeah.
Won't you take?
Yeah, when you subtract. Okay. So
you would start at the tip. What I'm getting at is you would start at the tip of u. And then you take the tail of v, and then it would go down instead.
You talk about this, right? Okay, let me draw it, okay? So you're talking about, would that be from here, and then you go down this way? Is that what you're talking about?
No, down like straight down like south. Because originally v is pointing upwards. If you're adding it, then you just go to where that tip is. But since you're subtracting v, wouldn't it go downwards? Because it's the opposite direction.
You want to comment? Want to draw here? Oh, you draw on your paper.
Yeah. So what you originally have, so this is the vector. So this is what you have for vector as u, right? And then v, originally if v is just this, if you're subtracting, you could just you add the negative v, and then it'd be downwards. But since you're if you're adding, you add from the tip to the tail.
Right? Okay. So got it. Okay.
It's going to be u minus v.
Okay. Let's do it. Okay. So you have u right here, and the opposite of v. Then let's do the opposite of v. So that will be going this way, right? This is opposite of v. Do you agree?
Yes.
Then the result here will be this way, right?
Yeah.
So this will be u minus v, right?
Yeah.
But they are the same, equivalent. Why? You see this? This is the same. Okay, let me highlight this. This and this are the same.
Yeah, I agree. They're the same vector, but like since you're specifying that, wouldn't it have to be specifically there? In that drawing.
Remember, the vector are equivalent. It doesn't matter the position, right? You move this vector down here. It's the same. Yeah, it's the same. They're equivalent. So it's the same.
I'm just asking, like, because notation-wise, wouldn't it make more sense? It goes from like the tail, and then here's the tracking. Notation-wise.
You see, as you can see here, notation-wise, u minus v actually. Oh, you mean the initial point of u to the ending point of to this the negative v? Yeah. But notation-wise, it looks like that way. But
still the same vector,
but they still are the same vector, equivalent. Yeah, good question. So these two are the same. Okay, so you can do it. So this, and this, we call them equivalent.
Yes, I agree.
Yeah. Okay. Very good. Okay, now we're going to talk about component. Okay, component of vector. Well, don't be scared. If you can do 2D, you can do 3D. You just need to add one more dimension, right? Okay, so don't be too scared about trying new things. So over here, the first one here, remember when you have a 2-dimension plane, then a vector, what will be a vector? Then a vector will be, see, this is a 2-dimension. Okay, let me make it larger. Okay, so this is on a plane. This is on R2, 2-dimension. Okay, so what happened over here? So on R2, then this, we have a vector on the plane. This is a plane, right? So this is a vector. Now, what does this vector do? It go from the origin and point this way and end it at this point, right? So what is this one over here? This is the point, okay? This one over here is a point. Let me write down. A point, this point over here is A1, comma A2. That's a point. Notice that what notation I use. I use parentheses, right? So parentheses and then the x coordinate, the y coordinate. That stands for a point. Now, how about a vector? Go from here to point to this point. Then I will have a different notation to indicate this vector. And I will use the angle bracket vector. Okay, so do you see? So the angle bracket over here, that is the vector notation. Okay. So, and now I should put A1 here, A2 here. So starting from the origin and point to this point, that is the vector. What's the difference between the two? The first one here with the parenthesis here is the point. The second one with the angle bracket over here is a vector. Do you see the difference? This is a point and this is a vector. Okay. All right. Now, similar for, yeah?
So we use that, but it's always in reference to like the coordinate system for any particular vector when written in component notation.
Yeah,
It's
in
always with
component.
reference to the origin of it. Vector has no inherent.
Yeah, if you put it this way, for example, 3, 4, that will be then that's the vector starting from the origin and point to the points 3, 4.
Okay, and it's always relative.
Yeah, but I will get to that. That's a very good question. I think I'm going to answer that in the next page. Okay. All right. So, and then now we get to 3-dimension, right? So this is in R3, okay? This is going to be in 3D space, right? Okay, and that will be R3, okay? All right, then now if you think about a point, how do you indicate a point in R3? You have A1, A2, A3. You have 3 coordinates, right? The X, Y, and Z coordinate, that's a point. When you use parentheses here, that's a point. And then what about if you want to indicate a vector? It go from the origin and then point it to this point. Okay, that will be a vector. Okay, that is a vector. And all you have to do is just replace this. You just replace this parenthesis here by angle bracket. So that's a vector. Okay, parenthesis for point, angle bracket for the vector. Okay, all right. Maybe here is a good place to talk about R3 and V3. Okay. I save it. Okay, I will get back to this. Okay, so now remember, this one here is a vector or point. Let me ask you, this one, vector or point?
Sure.
It's a vector, right? So those are the vectors. For vectors, those are called components. Okay, see, component. Those are the component, first component, second component. Okay, and this one here for 3D, you have first, second, and third component. Those are called components. Okay. Now, what's the difference between point? Okay, let me write it down. So if you have point, you have A1, comma A2, right? Okay. Those are not called component. What do you call them? Coordinate. Okay. So for points, those are called coordinate. For vector, those are called component. Oh, the aha moment. What? Okay, he did. Yeah. So coordinate, this first coordinate, second coordinate, those are points. And first component, second components, those are for vector. Okay. So for example, maybe just more example, okay? So if you have a point 3, 4 in parentheses, this is the x coordinate or first coordinate, right? And this will be the second coordinate, right? And now if you have vector, then you have an angle bracket like this. Then 3, 4, sorry, I should use a blue color. 3, 4, this is the first component, or you can call that the x component. And this will be the second component. Okay. All right. So the angle bracket make it a vector. Okay. Okay, those are the notation for vector. Now, what about this vector OP? Okay, so this will answer the question that one of you just asked about. Okay, so this vector over here, angle bracket 3, 2. So you will say, oh, is it always start from the origin? Let's have a look here. So 3, 2. So start from the origin and point to this point 3, 2, right? This is a vector, right? So you agree that that's a vector 3, 2, right? This pink one here. However, if you take this vector and move to different position, you get this, and this, right? This is a different position. But remember, the position doesn't matter. They are all equal. They're all equivalent. So those are the same vector. When I first studied this, I said, oh, they're different places. How come you said, well, we call them equivalent, okay? So all of this represent this one, all of this vector over here, all of those vector, all those vector over here have the same representation, 3, 2. Yeah? You consider them as this 3, 2. So it doesn't have to start from the origin. As long as you point to the same direction. Someone say, oh, how do I know 3, 2? Well, you just go 3 unit to the right? You S3, and then you go 2 unit up, and then the result will be the vector. Okay, so this just means that you go 3 unit to the positive x direction, and then 2 unit to the positive y direction, and then this is a vector that you have. Okay, so it's always 3 and up. 3 and then up 2. Okay, move 3 up 2, move 3 up 2, move 3 up 2. Do you guys see it? Okay, so they're the same vector, 3, 2. So it doesn't have to start from the origin. Okay. Okay. So so as I stated here, all those vectors are equivalent to this vector 3, 2. Okay. Yeah. So you can just think about starting from the initial point, you go 3 unit to the right and 2 unit up, and then then you have one representation of the vector 3, 2. Okay. So all of them represent 3, 2. All of them. Okay. All of them are this. Yeah.
Which also means many more lines can still represent them.
Yeah, there are many more. Those are just a few examples. There are infinite many representation of this same vector. You can put it over here. Okay, so you can put it start from this, and then you go 3 units to the right, 2 units up. Then you will get this. This is also another representation of this vector.
As long as the condition meets, how will it be represented?
Yeah, as long as you from the initial point, you go 3 units to the right and then 2 units to up. Then this vector here is a representation of that one. Yeah, the infinite many representation. Okay, and then just think about it's like your iPad pencil, your Apple Pencil here. You move it different places. You still consider them equivalent. It's the same pencil right here. Okay, so 3 units. Okay, right here. So you have 3 units to the right and 2 units up. It's still the same pencil, okay? The same vector right here. Okay. All right. Yeah. When I first started that, I have trouble saying, oh, they're all different places, but they consider them as equivalent. Okay. That was a 2-dimension case, right? What about 3-dimension case? When you have 3 components, right? Okay. Now, what do you think? What do you think about these 2 vectors? Are they equivalent? Yeah, from the look at this, looks like they are equivalent, right? It's okay. Equivalent is kind of like if you move them, okay, you shift them, they're going to coincide each other, yeah. So if this is like a stick, you move it, and then it's going to coincide with this one. Them equivalent, okay. It's like a pencil here, okay. So it's like you have this. So it's like you have this pencil here, and you move and move, and then it's going to coincide with the other one, then they're equivalent, okay? So same vector. Okay, so they're the same vector, okay? Now, but which one? So this A1, A2, A3 is the position vector of this point here. Okay. Notice I use the angle bracket notation, right? Okay, so now this is a larger picture, right? So these 2 are actually equal, okay? Now, given this, okay, how about if you move this vector to here and starting from this point x, y, z, then what will be the ending point of this vector that's equivalent to this vector? All you have to do is what? The x coordinate, the x component. So for this ending point here, what are you going to do with the x coordinate? You're going to add what? A1, right? You add A1 to the first coordinate. You add A2 to the second coordinate. You add A3 to the third coordinate. Okay, that will be the ending point of this of this vector. That's equivalent to the one that you start with, right? Okay. So for example, let me give you an example. So suppose the initial point. Okay. Let's say this one here is this point over here is say 5, 3, and then 1, right? This ending point here, suppose, okay? This is an example. Then this one here start from, okay, let me say it start from this point 2, 4, 6, okay? Suppose that is for A, okay? Then what will be, if I want to get the equivalent vector of this one, this vector, what will be the ending point? Then the ending point over here will be what?
X plus 5.
Yeah, 2 plus 5, right? You add 5 to it. Yeah. And then you have 4 plus 3.
7, 7, 7.
Yeah, right. You got it. 6 plus 1. You just need to add. You just need to add this one. Okay. Just add that to the initial point. Yeah.
Why not just stack them on top of each other?
Oh, that was when you, oh yeah, you can stack, that was that geometrically. So when you stack them, oh, you add them? Oh, you're not adding vector right now.
Well, the 5 is like stack on top of the 2 or 2 stack.
Oh, yeah.
That's the stack.
Yeah. Oh. Okay. So rhythm say that, oh, why not just do it this way, right? So you have 2, 4, 6, you stack them up. So the last one that we saw here will be 7 and then 7, 7, right? You add up the component. Yeah. Yeah, you got it. Okay. Yes.
It says position a vector P, but P is written with not with an angle bracket. So that like
Oh, it's a position vector. So position vector of P is actually this vector. This is actually OP. The vector. Position vector of P is actually OP with the arrow on top. It's this vector. That's the position vector. Position vector is a vector with initial point and a terminal point. And the position vector of this point, position vector of this point P always start from the origin. Start from origin and point to P. That's the position vector. So position vector this is actually 5, 3, 1. Say if this way. That's the position vector.
oh, and then that's just the point.
The one with the parenthesis is the point. The one with the angle bracket is this. It's the arrow. The arrow here is this. It's a vector.
So then we example like flip out, the vector is going to be the same and the position is going to be the same.
Yeah. So if you move the vector, you move this. Think about it as a stick, right? You move it other places. Then it's kind of like this one, right? It's a different position, but it's considered as an equivalent to this vector.
So for the is also vector.
Yeah, they're equal. Yeah, equal. So OP and AB are equal. The two vector, the equivalent. Yeah. Think about the pencil. They're equal. Okay. Yeah, the position. I mean, they are different places. Yeah, but in space, they consider as equivalent. Yeah. That was one of the confused things that when I first started, I said, oh, they're different places, but they're considered equivalent. This one and this one equivalent. Okay.
So can you say that you added some because that's the same vector, you can't say that you added something like there's no way to describe how would you describe the movement of P? Like would you need another vector to describe
Oh yeah. So for example, so this one starts from 2, 4, 6. And then you just add the component to get the terminal point, then you get the equivalent vector.
If you wanted that vector in space, you could say it's the vector 5, 3, 1 plus the vector 2, 4, 6.
No, it's not the vector. 5, 3, 1. This one here indicate what does it indicate? This one here indicate the direction. The 5, 3, 1 indicate direction. So that means the first component you're going to move 5 units to right, and then you're going to move along the y direction. You're going to move 3 units. Right? Along the z direction, you're going to move 1 unit. This one here is it gives you the direction. Yeah. So for example, if you start from a different point, suppose you start from 0, 5, 9, right? Then how do you get the equivalent vector? Well, you just need to add. You just need to add 5 to this, add 3 to this, add 1 to this. Then you get the ending point, and then you will get this equivalent vector. Then you will get 5, 8, 10. Then this vector starting from this point and at this point, this vector is equivalent to the one that you start with. So you can pick any initial point. So it doesn't have to start from the origin. You can pick this point, any initial point. And how do you get an equivalent vector of this vector? You just add each component with, so add this to get the ending point, right? Okay. Okay, let's look at the example. Example 3. Can you find the representation, vector representation of can you find the vector represented by this directed line segment with this initial point and this terminal point? Can you find a vector? Think about it. Okay.
-4, -4, -4.
Right. So the vector AB, okay, I'm going to put an arrow on top, okay? The arrow on top that indicates a vector. That's equal to, remember that's a vector, so you use angle bracket right here, and let's figure out the component, okay? Right? So, yeah, actually, let's go back to the last page. We haven't filled this out. So the vector AB, so given this, right? So given A x1, y1, z1, B x2, y2, z2. So what is the vector A? Would this represent the vector A? How do you represent the vector AB? What do you do with the component? What do you do with the coordinate? Huh?
X1 plus X2.
Plus or add? Minus. Yeah, plus. Yeah.
X2 minus X2.
You got it. Good job. That should be subtracting x2 minus x1, and then what? y2 minus y1, and then g2 minus g1, right? Yeah. Take a look at this picture. Yeah, take a look at this picture here, right? So you would take the ending point, okay, the coordinates, and then subtract the starting point coordinate, and that will be the vector, right? So this one subtract this one, you get 5. This one subtract this one, you get 3. This one subtract this one, you get 1. And the 5, 3, 1 is a vector that represents this AB vector. Okay, so just remember. Okay, let me do this. So if you have A and then B, then all you have to do is just take the x2, y2, z2, and then this is x1, y1, z1. Then this vector over here, remember this is a vector A, is going to just take x2 minus x1, y2 minus y1, z2 minus z1, and for each component of this vector, right? Yeah, Caroline?
Oh, did you say the x2 minus x1 and those things delta x, y?
You can say delta x, but then delta sometimes could be x1 minus x2, right? But make sure you use x2 minus x1. Yeah, the ending one subtract the starting one. If you reverse it, that's another vector point to the opposite. If x1 minus x2, then you change the direction to opposite, right?
So that would be
yeah, that would be BA if you change the reverse order. Yeah. So you take the ending one, subtract the initial one. Yeah. Okay, so go back to this one, right? So we have the initial point and the ending point. What do we do with the component? Yeah, terminal minus initial. So it's x.
Yeah.
Very nice. So that will be
You can still think of like X1.
-2. So that will be -2 minus what? -2, and then what? 1 minus -3, and then 1 minus 4, right? So the resulting vector here is what? -4, 4 and -3. Yeah, you got it. So it's very simple, okay? Don't think too complicated. So you're giving the initial point and terminal point to get the vector. It just take the ending. Take the coordinate for the ending point, subtract the coordinates, the initial point. Okay? Then you get the vector. Okay. So not too complicated. Okay. Don't over complicate it. Okay. Okay. Take a break. Okay. Let's take a break. Okay. Now we're going to talk about the magnitude or length of a vector. Okay. So what is the magnitude of a vector? Right. So remember, a vector has magnitude and direction, right? Okay. So we often indicate by an arrow, okay? So what will be the length of it? So suppose this is a two-dimensional vector, say A1, A2, right? So let me put it over here. So this point over here is parenthesis A1, A2. Okay, and the vector over here is this. This is a vector starting from the point 0, 0 to it could one representation is starting from the point 0, 0 and then point to A1, A2, right? Okay. So what will be the magnitude? In other words, how long is this vector? By the Pythagorean theorem, what do you think? Or by the distance formula? Yeah, you got it. Okay. So that is the square root, right? That is the square root of what? Yes. A1 square adding A2 square. Yeah, you got it.
Dot, dot, dot for all.
If you have more dimension, you just keep on adding the square of each component and then sum them up, right? You got the idea. Okay, good. So the next one is this is 3 dimension, then you square the component and you sum them up.
So length and magnitude are referring to the same thing.
Yeah, in this case, length and magnitude refer to the same thing. Yeah. I can't think of it. Well, in just this think about it as a set, okay? In this class. Okay, now we just talk about how to add vector geometrically. How do we add vector geometrically? We have 2 laws, right? If you add them geometrically, then what do? You can have the vector u, and then you have the vector v, right? And you add them up. One of them is the what? The triangle law, right? Triangle law. Or you can use what other law? Parallelogram law, right? The parallelogram law, you go this way, this is the u, and then this is the v, and then you get a parallelogram, and then this diagonal over here is u plus v, right? Okay, so that is you add the 2 vectors geometrically. Okay, geometrically you add them using one of these 2 laws. Now, what about you add the vector algebraically? Well, that is even easier. So if you have this vector and this vector, then when you add them up, you just add the component. Yeah, you just sum you sum the corresponding component. That's it. Okay. So and it's for the cases positive, right? So you just sum the component. Okay. So add the corresponding component. That's how you add it algebraically. Okay. Let's look at some example. Yeah.
So are vectors and matrices basically equivalent since
vector.
Just like it's
Oh, you can think of the vector here. It does look like a matrix, but it's like only a 1 by it only have 1 row. Yeah.
But it's very simple.
Oh, actually, you can think about the vector here, it's kind of like one row of the matrix. Yeah, one row of the matrix. That is a good observation. We're actually going to connect vector with a matrix later on.
It's about 3 or you have to wait for.
We do a matrix. Yeah, we're going to do a matrix. Wait, you don't, yeah. So
Exciting.
coming, yeah, getting excited already, huh? So just wait, we'll get to that, right? Very soon.
Is there a difference in the order there? Is it?
The order pair, the order doesn't matter. Oh, but when you add them, the sum A plus B or B plus A is the same, isn't it?
But is this the same as like in physics or like in vector components or like I and J? This is a big sense.
Oh yeah. The first component is kind of like the I, and second is for J, and the last one is K, right? Yeah, you got it. Huh?
No. When they do that, it's just like convention, and is it referring to the exact same thing? Difference is there actually different?
The first component is the X component, Y component, Z component, and then we get to the IJK part, but don't worry, we get to that. I'm glad that you connect this with physics. Yeah, I'm gonna see it. And here is a picture explaining why. Yeah, A1 A2 A1 A2 plus B1 B2, and as you can see that's for A. Okay, and then adding B. Then B has B1, B2. Then the result of the two vector is actually as component A1 plus B1, A2 plus B2. This diagram explains it. Okay, you can see that here is the X components A1 plus B1, and the Y component will be A2 plus B2. Yeah. Okay, now let's talk about component. Finish this. So the two triangles are similar triangle, right? They're similar triangle. Yeah.
Give me the diagram.
It's in the note, right?
No, I was going to take a picture of the guy.
Oh. Okay.
The guy, you know.
Okay, sure. Okay. Okay, these two are similar triangle, right? So if you scale the vector A, and then you get this, right? Multiply that by C, you get a scalar multiple of A, this vector. So start with vector A, and then multiply by C, you get this. Then it's the same as you multiply each component by C. Multiply A1 by C, multiply A2 by C, same thing, okay? So let's fill in the blank, okay? So you got A and B. What's A plus B? Let's fill this in. The first component will be what? A1 plus B1, and then A2 plus B2. Yeah, you add the corresponding component, right? What about A minus B? Yeah, you subtract the corresponding component, right? Subtract. So A2 minus B2. What about C times A?
A1, CA2.
Yeah, so that will be CA1, and then you just use C to multiply each component. Okay, CA2. Yes, you got it. Good job. Similar for 3 dimension, right? Okay, so just quickly fill that in yourself, right? So very similar idea. For 3-dimensional vectors, and if you add the 2 vector, you add the corresponding component, and subtract 2 vector, you subtract the corresponding component. Scalar multiple of the vector, you just use the scalar to multiply each component. Now, do you guys remember what's R2? Do you guys remember R2? What do you? Yes. R2, or you call that R cos R, right? Which is, so R cos R, okay, we call it R2. It's a plane, right? So it's going to be a plane, 2-dimensional, right? It's going to be a plane. Now, if I try to write out the element on the plane, what are the elements on the plane? So that should be a point, right? So a point over here has X and Y coordinate, okay, such that X and Y are real number. X, Y belong to real number, okay? So that is R2. R2 is a plane. is a connection of all the points. Okay, so say I have a point over here, that will be x comma y, and I have so many infinite many those points, and I'm putting they put together is the plane, right? So the element on the plane is a point, right? Now, yeah.
So for the when you say it's x and y are inside of R, do you have to use the set inclusion or whatever for x and y, or do you have to difference it? It seems like x is like not defined to be inside of the set, and then y.
No, it's a custom that just put x, y. So you can put x, y, z. It's okay.
Okay.
It's okay. That all of them belong to R. Yeah.
Okay.
Okay, very good. You can even put x, y, z belong to R and say, yeah. Okay, good. Now, this another notation here is called the V2. Okay, V2 over here. So what is V2? V2. What's the difference between R2 and V2? R2 is the two-dimensional plane, right? Element will be the point. Then V2 will be, take a guess. V stands for vector. Okay, so the component here will be vector. So instead of using parentheses, I'm going to use angle bracket, and then I will put x comma y. Okay, such that what? XY belong to XY are real number. Yeah, same thing. So what's the difference between R2 and V2? What are the elements in R2? Those are what? Points. Yeah, those are points, right? And then what about in V2? What are those? Vectors. Those are vectors. So this is like connection of vector. Okay, let me try to draw it to you. And so right here you have. So what are the vectors? So this vector could then this vector could be this vector could be this vector could be all those. Okay, so this is V2. Okay, the difference here is the element in R2 are point, the element in V2 are vector, two-dimensional vectors. Two component vectors. Okay, two component vectors. Okay, and then similar with R3. Okay, what's R3? It's a 3D space. What are the elements in R3? Points, X, Y, Z. Okay, what about V3? Right. Yeah, vectors. That each vector have how many components? 3 components. Yeah, you guys got the idea. Good job. Okay. Now let's talk about component. Continue with this. Okay, some property of vector. Well, here is a. Maybe I'll give you one more example first. Okay, this example. Example. Could you find the sum of the 2 given vector? So this vector is -2, 8, and the other vector is 6, -1. What is A plus B vector? What do you do with the component? When you sum them, you add the component, right? So you will have -2 adding 6 and 8 adding -1. Then that will be 4, 7. Yeah. So actually, algebraically, it's very easy, right? You just add the component. I think geometrically it's a little bit harder. You have to move, right? You can either use a triangle law or the parallelogram law. Okay. Huh?
On the A equals A1, is that just saying that?
Oh, here. Let's read this. So this one here is a vector, right? It's a vector. It's a vector has how many components? N component. Okay. So those each one here, okay. A1 is a 1 component, A2 is a 2nd component, etc. Just extended that, okay? So extended to n dimension, then you have n component. Yeah. Actually, some people say, oh, how can you imagine n dimension? Well, think about when you do cooking, right? You have how many ingredients, right? You can have n ingredients, or you sometimes have 10 ingredients, right? So you can the first ingredient, how much you put on that, second ingredient, this. So you can have actually 10 dimension things for like when you do cooking, okay? Okay, the property of vector, well, it's commutative. A plus B and B plus A are the same. It's associative. You can associate B plus C first or associate A plus B first. If you add zero component, if you add zero vector, it doesn't change the vector. If you add the opposite vector, it cancel out, you get a zero vector. Scalar multiple times the sum is the same as a scalar times each vector and sum them up. And then also this one, you can add the two scalar first, or you can take the scalar times A and then sum them up, right? And then also this one, and 1 times the vector itself is the vector itself, right? So those are kind of intuitive, right? And I'm not going to prove it. You can see that, okay?
Can I take a picture first?
Okay. This one?
No,
This
that's where you
The properties.
This one? Okay, sure. I'm going to make video. You can look at the video and take screenshot of it. Do you guys want to stay longer? Okay.
Why is CP in the parentheses multiplied by?
Oh, okay. Let me give you an example, right? So for example, like 2 times 3, and then times this vector A, then that is the same as 2 times 3 times the vector A. Do you agree?
Yes.
Yeah, so you don't need proof, right?
Yes, I mean, totally.
It's so
If you remove the parentheses, nothing change, right?
yeah.
So what's the point of it?
Oh, but you agree it's true, right?
Yeah.
Okay, good. Okay, now this is the IJK that you were asking about. Okay, now there's 3 special vectors in V3. Remember V3, right? The element will be vector, 3-dimensional vector. These 3 you should pay special attention to. Those are the IJK vector. Okay. Let's start with 2 dimension. Okay. So this is in V2. Okay, this is in V2. V2. Okay. Then the vector I will be this vector. The first component will be 1. The second component will be 0. It's this vector pointed this way. Yeah. And then the vector J will be this. Okay, the J will be this one. This is the J. Sometimes they instead of putting arrow, they put J and put a hat. Okay. These 2 are the same. They represent this vector J. Okay. So the second component will be 1. The first component will be 0. Okay. So this is the I vector, or you can put I hat, or you can put the arrow. It's the same thing. This one here is the same as J, the arrow. Okay. So those are the 2 vectors that kind of it's called the basic vector. Okay. Standard basic vector. Okay. So what do you call that? Standard basic vectors. Okay. So in the x direction, this one here in the x direction is 1, right? This one in the y direction is 1, right? It's a standard basic vector. Now in V3, okay, so V3, then what is I? Okay, let's put it down. So what's I? This vector is equal to what? Put down the component. 1 will be the second component. 0, 0. J will be what? 0, 1, 0. And then K. You got it. 0, 0, 1, right? Okay. So as you can see in the picture, here is I, here is J, here is K. What are the magnitude of each of this standard basic?
One.
One. They all have magnitude to be one. So something called a standard unit vector. Okay, vector. Standard base vector. Okay. Anyone need to take a picture? Okay. All right. I'm gonna make a video. You can take a screenshot. Okay. Okay. Yeah, we'll try to get it. We'll try to leave here in time. Okay. We still have a couple pages, 7 more pages to go. Okay. All right. Okay. Now, component. So if A equal this, so those standard basic vector is going to help you to write a vector. Okay. For example, the vector A, you can, if the first component is A1, then you can put it as A1 times I. And then second component is A2, you can put the A2 times J. And then here we can put A3 times K, right? Let's try to put express this in terms of IJK, this vector. What would that be? How many I should I put?
One.
Yeah, one I. Yeah, just I, right? Okay. And then what? Minus 2J. And then plus 6K. Yes, you got it. Okay. Sometimes maybe it should be consistent. If you use arrow, use arrow. If you use hat, use hat. Remember this is the same as this. If you put a hat there or you put that, this is for the unit, standard unit vector. Oh, sorry, not that K. Okay, J. And then K, just different notation, okay? Similarly, you can write this here as, well, that would be what? If you use standard basic vector, that would be A1 times what? I, okay? And then adding A2 times what? J, yeah, you got it. Okay. Right, moving on. Okay, here's explain the interpretation. Okay, now we're going to talk about unit vector. Unit vector here, well, as you know from the name, what's the magnitude of a unit vector?
1.
It's 1. Now, if you have a vector, how can you scale down or scale up so then the magnitude will be 1? You can, what do? You can divide the vector by its magnitude, right? So if you divide the vector by its magnitude, then the result will have magnitude to be 1, right? Okay. So divide by the magnitude, you'll make it a unit vector. Okay.
So division is the unit vector.
Huh?
Division is the unit vector.
Okay, let me give you example then. So suppose you have this vector A, right? This is the vector A. Okay, and suppose the magnitude over here is say 5. The magnitude of this is 5. Right? Then how can I get the unit vector in the same direction? Then you will divide this vector here by what? By 5. Then you will get the unit vector. Yeah. Then you will get this. So divide that by 5. So this vector here, divide by 5. Then you will get this unit vector here. The unit vector in the same direction, right? Yeah. Okay.
They're just getting them 1.
Huh? So then you make the magnitude to be 1. Yeah, so you scale down to have magnitude to be 1.
So is U the unit vector?
U is a unit vector, stand for unit vector. Yeah, the U over here is a unit vector, okay?
Is this just to get a vector with magnitude 1 that's in this direction?
Yes. Okay, application, vector, can I ask someone to read this? Can I ask Rhythm to read this?
Vectors are useful in many aspects of business and engineering. Here, we look at the forces. A force is represented by a vector because it is both magnitude, potential, and bouncing and the direction. And several forces are acting on an object. The result force driven by object is vectors and this vectors. Vectors.
Okay, very good. Okay, thank you. Okay, now this example here. Yeah.
So if you have the unit vector, would you call that normalizing the vector?
Normalizing.
Normalizing it so that its magnitude is 1, so that like if you had a bunch of vectors and you want to perform operations on them, like is
normalizing. Yeah, I heard of that name before. I remember now. Normalizing doesn't mean that make the magnitude be 1. I
think so. Well, that's what I'm asking.
Hey, could you find it out and put it in the discussion? Because I am not 100% sure. Normalizing means that. Yeah.
Normalizing. That's what I thought.
That sounds so familiar to me, but on top.
Graphic processing, you are like, you know, like different like math, like code. When you're coding with vectors, you want to usually normalize them for different applications. Because like the magnitude doesn't contain useful information in the later direction.
Yeah. Yes. I think that is a very good question. Good point. Yeah, normalizing. So I don't want to give you false information. I need to look it up, or you can look it up too. Okay. Yeah, that sounds very familiar. Okay, now what do we have? I'm gonna ask Caroline. Could you read this?
A 100-pound weight depending upon 2 wires as shown in figure number 2. Find the tension forces P1 and P2 both wires and the magnitude of.
Oh, okay, very good. Okay, let's think about this. Okay, so let's try to understand what's going on. So right now we have this 100-pound, right? This is 100 pound, 100 pound weight hanging over here, and then you have the 2 cable, right? This cable and this cable. So it has the tension that going this way, right? Here, go along this T1, and then T2 will go this way. That's T2. Okay, the 2 tension. Okay, those are the forces. And the question over here, they try to find T1 and T2. Okay, and they give you the angle here, 50 degree and 32 degree. Can you find the tension along each cable, T1 and T2? The tension T1 and T2. Okay, so here is related to physics, okay? So remember when we do this kind of physics problem, we break it into component, right? Yeah, so you break it into the X and the Y component, okay? So now T1, let's think about T1 first, okay? Here's T1, that's T1, right? This tension, okay? If you break it into component, okay, so that will be this component, right? And then along the x-axis, it will be this component, right? And then along the y-axis will be this component, right? You break it into 2 components, one along the x, one along the y, okay? Now, the magnitude, okay? So the magnitude of T1, how do you represent the magnitude of T1? The magnitude of T1 is this, okay? So the magnitude of T1 over here is the absolute, you put the absolute value sign there, that stands for the magnitude of T1. Okay, that is the magnitude. TUD, right? TUD. Or you can call that the length. How long is it? Okay, magnitude length. Okay, so this is how long this one is. Okay, now and then for T2, you also try to break it into 2, right? Okay, so this is T2. And then you can break it into 2 components, one along the X and then one along the Y direction, right? Okay. Now let's try to think about this one. What is this component here? T1, the first component T1, right? The T1, the component along the x-axis. What will be this component? How long is it?
The cosine.
Very good. Okay, so you would take the magnitude of T1, right? You take the length of it, and then you multiply by, yes, very good, times cosine of 50 degree, right? Why is it 50? Because this one here is 50 degree, which means that this angle here is what? Also 50 degree, right? Okay, so this is going to be 50 degree. Okay. Oh, okay. Make it larger. Okay. So this angle is 50 degree. Okay. This angle here is 50 degree. Okay. Then you can see that there's a right triangle over here, right? Let me see what else. So the in this right triangle over here, okay, this right triangle over here. This is the adjacent side of this angle, 50 degree angle, right? So to get the adjacent side here, you take the hypotenuse and you multiply what? By cosine of 50 degree. Yeah, you got it. Because adjacent side over hypotenuse is cosine, right? So you multiply this hypotenuse, the length of the hypotenuse times cosine 50 degree is this one, right? Now I'm good. So that is the magnitude of this component. This component is pointing to the left. Remember, pointing to the right is the positive x direction. So this one here is pointing to which direction? The negative direction. So we should put a negative sign in front. Okay? Okay, so that will be this. All right, so this component will be negative. It will be this expression, right? Now let's try to find this tension along the y direction. Let's find this component, okay? So what will be the magnitude? Not necessarily 100. Okay, so you take a guess. Not yet, not 100. Not yet. But that is a good point. You kind of see the 100, but then you see T2 also had this component, right? So this 2 should add up to 100. So they shouldn't. So the green one alone shouldn't be 100 because it's the sum of this 2 should be 100. Yeah. Okay. So let's think about this the green one here. This one. So it's a same as before. It's in this y triangle, and this is 50 degree. So this one here is the same as this one, right? So if you know the hypotenuse, how do you find this side that is opposite to this angle? Sine, yeah, you got it. So for this one over here, that will be the magnitude of T1. And then you just say that multiply by sine of 50 degree. Yeah, you got it, right? Okay, good, you got this. Now, so T1, if you break it down into component, right? The first component, the x component, we have this, right? So let me write it down. So the x component will be negative. So that's the x component. It's along the I direction. Okay, notice that there's a minus sign here because it points to the negative direction. Okay, and then on the z component, right? The y component will be this one. And then that will be multiplied with sine of 50 degrees. You got it. Good job. Okay. Now, since you're doing so well, how about you go ahead and decompose the T2 into the x and y component. So in the x component will be what? The magnitude of T2 times what? Cosine of 32 degrees. You got it. And then the y component magnitude of T2 times what? Sine of 32 degrees. You got it. Good job. Okay. All right. Very good. Now, notice that the result of these two tensions, remember, look at the picture. Yeah, this is at rest, right? So that means the T1 and T2 counterbalance the weight, right? So that means T1 plus T2 equal to the weight. Yeah, the mg here. The weight is pointing down over here, right? Okay, so it's going to be the opposite of this W. So it's equal to 100 pounds, right? So we have T1 plus T2, T1 plus T2, this two vector, this two tension is going to counterbalance the weight. So it's equal to the opposite of the weight, which is 100 pounds, right? Remember?
Why is T2 not negative? Oh,
T2 is not negative.
it's not negative.
T1, then why is T1 not negative? T1 and T2 are basically,
Correction.
yeah,
So
yeah, the T1 go this way, T2 go this way. Both of them are not negative. Those are the vector, go this way, yeah? One go this way, one go this way, yeah. Okay, so, okay, so, okay, a good question here. So T1 go this way, right? You agree? T2 go this way, right? You agree, right? Okay, and then the way go this way, W go this way, right? You agree, right? Then T1 plus T2 is actually counterbalances. This is opposite of W. Do you see the?
Combined forces reverse.
Yeah. You see this two, T1 and T2, if you combine them, it should be opposite of this way, right? It go this way. So then this two counterbalance, right? The weight pull down, and then this one counterbalance it, so it should go up. So T1 plus T2 should be this one up. It's opposite of the weight. Yeah, that's equal to 100 pounds. So this is 100 pounds. Yeah. So and it's going this way, going up is positive. So it's positive 100J. It's in the J direction, right? So positive. Any question? Okay, let's do this.
So that's just the general form. There's no number.
I didn't put the number in yet, but the next step I'm going to put it in.
So why is it J I?
The weight over here, right? So 100 pounds, if we're going down, so this will be, this one here is negative 100J. You agree? Well, negative 100.
This J is
J, remember J is pointing up, not J's. Okay. Diamond. Remember IJK? This is I, this is J. Huh? Shouldn't. Oh, this is not 3 dimension. It's actually 2 dimension. Okay, this is 2 dimension. Okay, so so this is I, right? And this is J, right? So going down is negative J, going up positive J.
Oh.
Aha moment.
So the vertical axis is for weight, and the ones that go off the side for the distribution of weight. J and R's.
Yeah, those are the tension right here.
Is the W is minus 100J? Is that that's because it's going down?
Yeah, it's going down. It's you see, going up is positive
because it's gonna go on top.
Yeah, this one on top. Okay, negative W. Yeah, negative W here is equal to positive 100J. Yeah, it's going up as 100 and it's going to the positive direction. So 100 pounds up here. This one here is way down, okay? And going down is negative direction. So it's negative J.
So J here representing the vertical axis.
Yeah, you got it. You got it. Good job. Okay.
I is in horizontal.
Yes. Okay, now I'm going to put the number in here, okay? So now we have this, right? What do we have? We have T1 plus T2 equal to 100. So you have T1 plus T2 equal 100J. Okay, those are vector, right? How do you add two vectors? So this is the first vector, the second vector. When you add them algebraically, what do you do with the component? You add the component, right? Let's add the I component, right? So along the I, the horizontal direction, you add the two components. So that will be what? This one here, adding this one. Yeah, this one, adding this one. So I'm going to just copy this. So that will be opposite of T1, make it T1 times. I better write a little bit smaller, and you guys try to write smaller so then you don't run out of space. Okay, that's along the I direction. Okay, what about the J? Well, I'm gonna add this two component, right? So this and this, okay, add the corresponding component, add this one and this one. You guys agree, right? So you add the two corresponding component when you add the two vector, okay? Now, and that should be equal to 100J, right? It's 100J. So what does it mean? What does it mean? What does it mean? So this is J and this is J, right? So the result here has no I. So what do you know about this?
Has to be 0.
It has to be 0. Yes, it has to be 0. So this has to be 0. This has to be 0. And what will be this? This has to be what? 100. Yeah, you got it. Now we can just copy this. So we got this equal to 0, right? Then, yeah, so the second one equal 100. Then notice that over here cosine 32 degree and etc. Those are the number, right? How many variables do we have? We have two variables, the magnitude T1 and T2. Are we able to solve for the magnitude of T2? Can you solve this? Can you actually, from the first one, can you solve for magnitude of T2? And what does it equal to? So from here, you will have the magnitude T2 times cosine of 32 degree, and that's equal to what? Positive magnitude T1 times cosine of 50 degree, right? Agree? Okay. And then if I try to solve for magnitude T2, I would divide both sides by what? Cosine of 32 degree. Therefore, and from here you will get, that is the result here. That's equal to this, right? Okay. That's the magnitude of T2 here. And then you can substitute this into the second equation, and then what do you get? Okay, so T1 times sine of 50 degree with this one, and then the T2 is going to replace by this. So you take out, yeah, so cosine of 50 degree times sine of 32 degree divided by cosine of 32 degree, right? And that's equal to 100. Do you agree? Okay.
Why is that?
Here, the 0. Why is this one equal to 0?
Why you said that? We know the 100 is great, but what is it?
Okay, remember here, the A has to be matched with 5, B has to match with 6, right? So what's the A here? So this part here is this times I plus this times J equal to 0I plus 100J. So which means that this has to equal to, so it had to match with the 0. So that has to be 0 because there's no I.
That part had to be 6. Besides 0 is because it's canceling weight, because there's no weight, there's no negative weight. Right?
If you look at the picture, you can actually see that the result the result of T1 and T2 along the x direction is going to cancel out. It's not moving left or right.
Oh.
You only go up and down. Yeah, it's not left and right. So left and right has no the component cancel. So it stay here. Okay. Okay, so now, so T1, okay, and then after that, you can solve for T1, right? So T1 is equal to what? According to this equation, that will be what? 100, right? 100 divided by, divide by this whole thing in the parentheses, right? Yeah, you got it. Okay, divide by this whole thing in the parentheses. I'm going to just copy it because easier that way. Okay, divide by this. Okay, divide by that. And just punch in the calculator, and that should be about 85.64 pounds. Okay, so you find the magnitude of T1. How do you find the magnitude of T2? Substitute here, right? Yeah, substitute here. So remember this one. Yeah. So substitute here. Okay, we're going to substitute the result. Okay. Then you calculating, there's about 64.91 pounds. Okay. But those are the magnitude, right, of T1, T2. But what about T1 and T2? Well, if you know the magnitude, remember we break it into the component, right? Okay. Remember the first component of T1, okay, remember this one, right? The T1, along the x direction will be the first component. This is second component. If you know the magnitude of T1, you can just go ahead and substitute here and here to get T1. If you know the magnitude of T2, you substitute here and get T2. And this is what we have done. So T2 equal to this. Yeah. So we substitute the magnitude T1 and T2 into the two equations that we had before, and we get T1 and T2. Okay?
Wait, so when the problem says find the forces in T1 and T2,
this is the one.
Find T1 and T2, not their magnitude.
Not the magnitude. Yeah, they want to find T1 and T2, not just the magnitude. Magnitude is just how long is it, but the direction also matters. So when you find T1 and T2, you mean you try to find the vector